So we're going to talk about molecular dating with Mega. And so first of all, molecular dating is the process of estimating the age of internal nodes based on nucleotides or on amino acid sequences. So this is a fundamental step to draw biological conclusions from molecular data. Actually, many of the evolutionary analysis we do today, we have to rely on a time tree. This is an example. This is a great ape's phylogeny. So we have the internal nodes and the root node of the tree. And actually, modern methods are free from the assumption of constancy of evolutionary rates. That is a strict molecular clock. And a lot of Bayesian methods are used today, mainly MCMC3 and BEAST. And actually, these Bayesian methods require many prior assumptions. Like for instance, prior to model the rate evolution across the phylogenetic tree, and many times you don't know which prior to use because you don't know if your data comes from correlated rate evolution or independent rate evolution. So there is a very useful new methods that was implemented in MegaX. So just for you to know, if you have molecular data and you don't know if the rate of evolution is correlated or not, you can use core test. That is a method to test for autocorrelation of rates, and the preprint is already online on bioRxiv. And more than that, the use of Bayesian methods require a large computational time and And that's why fast dating approaches are so important. And among these fast dating approaches, we have RelTime that was proposed in 2012 in PNAS paper, and RelTime is much more faster. So in this graph below, we can see the computational time of RelTime, and the gray line is MCMC3. And actually, this is the fast computation of MCMC3. There is the approximate likelihood calculation. RelTime is much more faster. So how does RelTime works? RelTime refers relative rates among branches. So it starts from the leaf branches of the phylogenetic tree, and so relative rate between sister taxa will be the ratio of their branch length, because the time of the common ancestor is equal, and it moves towards the root iteratively, assigning relative rates. And when calibrations are provided, it adjusts branch rates so that the estimated times respect the minimum and or maximum calibration bounds that you gave. And if you have no calibrations, RelTime will produce a relative time scale. So before molecular dating, the first thing you have to have is a phylogenetic tree. But how to estimate a phylogenetic tree? So there is this very useful protocol that was published in MBE in 2013 that guides you how to build your phylogenetic tree based on molecular data in Mega. And actually, we have previously very interesting talks about that, so they already happened. But anyway, if you don't know how to estimate that, this is a very useful reference for you to start. And many other software has been written to estimate phylogenetic trees like Female, Mr. Bayes, RaxML, FastME, and IQ3 based on maximum likelihood Bayesian analysis of distance methods. And the important thing is that the phylogenetic trees output by these programs can be readily imported into Mega, and you can estimate your time tree based on that. Well, it's the same thing. You can estimate the time tree, the phylogenetic tree in Mega, or you can use the phylogenetic tree that you estimate on these programs to estimate a time tree in Mega. So once you have the phylogenetic tree, that's the first thing you should have. And the other thing that we need to estimate a time tree are the calibrations. So calibrations are the temporal information that allow to convert time estimates to an absolute scale in calendar years. And they rely mostly on the fossil records. It can rely also on geological data, etc. This is a crucial step in molecular dating since the final time tree will depend on the calibration information you provided. And although complex, the task of choosing suitable time boundaries can be greatly facilitated by the TimeTree web resource. TimeTree compiles actually divergence times that were estimated by distinct molecular studies molecular dating studies across the tree of life. And although this is not a fossil database, it is extremely useful to begin a search for calibrations and to collect the estimated molecular times for a divergence of interest. So if you have a divergence of interest, TimeTree database is very useful so that you can go there and look for all of the studies that have been performed and estimated divergence times for that node. This is the TimeTree web site, the interface, and we will focus on this panel of TimeTree. So if you go there and type, like for instance, gorilla and Homo and click search, TimeTree will first try to resolve the ambiguities and will say gorilla is gorilla genus and Homo is Homo genus, and you click show time. What TimeTree will show to you is this beautiful panel with a lot of information from geological data, from oxygen levels, and etc. But what is important for us here is this table that will be shown below that actually lists all the studies that estimated divergence times for that node that you're interested. And in this case, I'm not showing all the studies here, but it's saying that it has like 55 studies. And this information here is very important because this is the median time among all the studies, all the dates that the studies estimated for this divergence, and this point here represents the ages of the nodes. And the other thing that is very interesting is this information that is the estimated time that was inferred on these two works, first on this one and later was further improved on this one. And it contains also information about the confidence interval for these estimates. That, for instance, for the divergence between gorilla and Homo will be a confidence interval, shows you a confidence interval that goes from 8.45 and 9.69. And the time information that is provided by TimeTree is a good starting point actually to obtain calibration information. And in particular, as I already mentioned, the confidence intervals may provide reasonable ages for minimum and maximum boundaries. And if we do the same thing for the divergence, we did that for gorilla and Homo, and by doing the same thing for the two species of chimpanzee, we get this confidence interval, this median time, and this estimated times. And once we have the phylogeny and the calibration boundaries, you are ready to estimate divergence times with RelTime in MegaX. And this will be the two nodes that we will calibrate here. So MegaX runs natively on Linux machines besides PCs, of course, and is currently being developed, will be released in the near future for macOS. This is the Mega website. You just go there and click download and follow the steps on the screen. It's very easy to install. And for this talk, we will actually use the example files that you download together with MegaX. And there are two important files that are this one and this one here. The first one, both of them calls mtcDNA. One is a MAG file, the other one's a Newick file. So the MAG file is a mitochondrial alignment data, and the Newick file is a phylogenetic tree of the great apes example that I have been showing you in the previous slides. And the point is that with these two example files, all the following steps can be performed in MegaX. When you start Mega, this is the main Mega window, let's say, and you just have to go there and click on this button here, that is the clocks button, and once you click that, what will appear to you is this panels, so you just have to click Compute Time Trees, and MegaX will show you three options. Which are these three options actually? So RelTime ML, RelTime OLS, and RelTime branch lengths are the three options, but what do they mean? So RelTime ML actually estimates the branch lengths by maximum likelihood. This is the original approach that was proposed by Tamura et al. In the 2012 PNAS paper. And this is simply the idea that you will compute the branch lengths based on maximum likelihood, which is a robust method. And RelTime OLS, the second one, estimate the branch length based on the ordinary least squares distance methods. This is useful for big data sets, very large data sets, because this is faster than RelTime maximum likelihood, and is also useful if you have a big data set with a good coverage, or that is without a lot of missing data. And RelTime branch lengths actually estimate the times based on a user-provided tree with branch lengths. This is useful when you have already estimated branch lengths under approaches different from maximum likelihood or OLS, or under models of evolution that are not yet implemented in Mega. For instance, the Lewis model for morphological data, which means that if you have a phylogenetic tree that was estimated with a morphological matrix, you can readily import that to Mega and estimate divergence times based on a morphological tree. But usually you are the most used option, actually. The option that we will use here is RelTime maximum likelihood. That is the original method that was proposed by Tamura et al. So just select RelTime ML, click that, and the TimeTree wizard will be open. This is a window that is called TimeTree wizard, and this is the window, actually the place where you will provide all the information, the relevant information to estimate your time tree. So I have several steps, and we will talk a little bit about each of these steps. First of all, you have to load your sequence data. It can be nucleotide or amino acid, doesn't matter. And just click browse, and you have to select that on this window that will open. As I mentioned before, we will use the example files that comes with Mega. This is the empty cDNA file. This is a MAG file, and you just click open. If your alignment file is not in Mega format, you have to change that to FASTA. So just go to the right bottom panel and change the showing option, that instead of showing Mega files, you have to choose showing FASTA files, and you'll be able to select your file. So the second step is loading the tree file. This is the tree file that you estimated based on the same alignment. So just click browse and do the same thing. Select the tree file. Here we have to select the Newick file that comes that we downloaded together with Mega, the empty cDNA Newick file. Just click open. Newick file is the standard file format for phylogenetic trees, to store phylogenetic trees, but some programs like MrBase outputs the final tree in Nexus format. If this is the case, so if your tree is in Nexus format, you have to export that to Newick in order to use that tree in Mega. So the easiest way to do that is to open your tree that is in Nexus format in FigTree and export that in Newick to a Newick file format. So this is very easy. Just open that and export as a Newick tree, and Mega will be able to open that. Okay, so we already loaded the sequence data, the tree file, and the next step is to specify the outgroups. There are two options to specify the outgroups in Mega: the select branch and select taxa. The distinction between them is only a matter of preference. You can do the way you want, but let's talk a little bit about each of them. So if you select branch, this window will open to you. So in this window, you just have to select the lineage that contains the outgroup sequences. In this case, the GBOM is our outgroup, so just click that, and Mega will highlight that in red, and the word outgroup actually will appear on the right of the outgroup sequences. So you just have to say OK, and once you say OK, but first of all, double check to make sure you define the outgroups correctly, because this is very important, since the incorrect specification of outgroups will compromise the whole analysis. And if you are pretty sure that you selected the outgroups correctly, just click this window will appear, just say yes. If the outgroups are not assigned correctly, just say no or cancel, and you do that again. And just say yes. Okay, so this the way we talked was the select branch option. If you if you want to specify the outgroup through the select taxa, just click that, and this window will open. In this our case, and I mentioned before, the outgroup is the GBOM. So just click the GBOM and click the left arrow, and Mega will include the GBOM as a taxon in the outgroup, and these are your ungroups taxa, let's say. So just say OK. Oops. just click OK, and your outgroup will be specified. Okay, so after selecting, specifying the outgroup, you have to specify the calibrations. Important thing is that, as I mentioned before, RelTime does not require any calibration information to estimate divergence times. And if no calibrations are provided, it will compute relative times without assuming a strict molecular clock. And if you select skip, RelTime will then provide your tree on a relative time scale. It can be very useful if you want to date, let's say, duplication events of gene family evolution, or if you want to estimate a time tree for a biological group where no information is available about calibrations or anything like that. But despite being valuable, relative time scale may not be meaningful in most cases, and we are interested here in estimating an absolute time tree. So we will not select skip, we will select add constraints, and when we do that, this is the window that will open, that is the calibration editor, as you can see. So it shows to us our phylogenetic tree, and we have to add a calibration point, we have to click on this signal here, that is this signal that is clock sign with plus. So this is the button that is called add a new calibration point. When you click that, you have to select the two taxa that you want to, that actually they have to correspond to a link to the most recent common ancestor that corresponds to the node you want to calibrate. In this case, I choose chimpanzee and bonobo, that are the two species of chimpanzee. And on this panel here, just say the minimum divergence time, the lower boundary, and the maximum divergence time, that will be the maximum boundary, to calibrate this node, and Mega will show to you the nodes that you are effectively calibrating, which is very important because sometimes it can be very confusing. And I did the same thing for the split between gorilla and humans. So this is the node and the minimum divergence time and maximum divergence time that I retrieved from TimeTree database. So just click OK, and you will have set your calibration points. And okay, so loaded sequence data, tree file, we specified the outgroups, the calibrations. So next, last step actually is to choose the analysis settings. So when you click that, we will open to you the window that is called analysis preferences. So for this, this is only the path to my tree file on my computer, and these are the RelTime settings. If you want to learn more about that, just go to RelTime papers. And important to us are the substitution model. This is substitution model you use to generate your phylogeny. So in this case, I select the general time reversible because it's a nucleotide data set. If you're using amino acid, of course, you use different models, but you have to select here on this panel the nucleotide substitution model that you use to infer your tree. And on the next panel, you have to say if you will use rates among sides, variation of rates among sides, and if it's gamma distributed or gamma plus invariant sides, and the number of discrete gamma categories. 5 is pretty good. And again, this will be based on the same substitution model you use to infer a phylogenetic tree. If you don't know how to do that model selection, you can just go to that protocol that I mentioned before, MBE, because all of the steps to select and test for the substitution model are described there, and it's very useful for you to learn. And the next panel is which data set you want to use. It relates to the treatment that you will give to gaps in missing data in your alignment. So you can use all sites or use the option complete deletion, which means that all the sites that have gaps or missing data will be deleted from the analysis. Actually, Mega will not consider that, RelTime actually. And the last panel, you have to set the number of threads. Of course, the higher the number, the faster will be the analysis, and it depends on the computer you have in your system. But for most analysis, one thread is pretty good for RelTime because RelTime is really, really fast. So once you set all of that, you just have to click OK. And when you click OK, the last thing you have to do is to launch your analysis. And by clicking this button, the progress window will be open, so showing this progress bar of your analysis, and actually some additional information like the starting time and etc. And when the analysis, when your job is done, the Tree Explorer window will be opened with your final time tree. So this is the time tree that we estimate based on that alignment and that tree and that calibrations we provide, and also the outgroup. So the outgroup is here in gray, and there is a divergence time scale below the tree that Mega will show to you, and of course the node ages will be displayed. And also the calibrated nodes, Mega will show that, will highlight that in red. Important thing is to save all the output files that RelTime produces in Mega. So once you click File, you have all of these options to save. My advice is to save all of the outputs, because you don't know if you will need that in the future for any other purpose, or to double check everything that you did before. And if you choose, let's say, export current tree in UWIC format, you have to select the divergence times options on the next panel, because if you select relative times, it will save your tree with no absolute scale. So, and you want that in an absolute scale. And just click OK, and the text file editor will open with your tree in UWIC format. To save that, you just click File and Save, and you can choose the name you want and save that on the folder you want on your computer. So important thing is to do that for all of the output files. You can do that also for the TimeTree in tabular format. There is all of the TimeTree information, but in a tabular format, which is very useful to open, is in Excel, for instance. The other one is the TimeTree in Access. So as I mentioned before, Access is another file format to store trees, and this is very useful if you want to open your tree in Fit Tree and color that according to any preference you have. And this is the analysis summary file. So just click File and Save As for all of this example, this output files that I mentioned to you. The analysis summary file is useful because it contains the start time of your analysis, and of course the execution time, peak memory, and the substitution model you use to generate that. This is very useful because sometimes we run that, and a long time ago we go back to the outputs and we can double check exactly what we did before. So save all of these files because it's very useful in the future. And another thing about the Tree Explorer window is that this is very useful because it has also a figure legend that describes the whole analysis that you did, and also have the citation of the references for the methods and models that you use. And in Mega you can save that too. So you can just click Caption and save it to text file, and you save your figure legend to a text file. And besides that, you should also save your time tree in an image file, because this is the easiest way for you to present that in your publication or in your thesis or whatever. And there are several formats that Mega allows you to do that. Of course, you should choose the image file you desire, but you can save that in BMP, PDF, PNG, and TIFF images. And this is the place where you provide the file name you want and just click OK. And for instance, this is an image file that I generated from Mega while saving the figure in PDF format. And so this is very useful because you have Mega provides you a image file and also the figure legend, so that you can use that in your publication or in your thesis, and everything comes very easy, and it's very easy to arrange the figures and put everything together on your presentation or wherever you want to. And lastly, all of the steps that I shown to you here are on this protocol that was published a few weeks ago in MBE, that is called Estimating Time Trees with Mega and the TimeTree resource. And we have on this protocol all of the steps I described, but besides that, more detailed analysis, mainly regarding Mega CC, which is the command line of version of Mega, and can be very useful if you want to run pipelines and simulation stuff. And so this is my email if you have any doubt. And with Mega or any help with, if you need any help with that, just let me know and I can try to help you. And I'll be happy to take any questions.